Yeah, so this is our method called Wave-CAIPI, and we use this for highly accelerated 3D imaging, and this gives us a reduced G-factor penalty. So recent modifications to Cartesian K-space sampling provides us with more robust reconstructions of highly accelerated K-space data. So for fully sampled K-space imaging with phase encodings in KY and KZ, we read out in the KX direction. We could undersample this by a factor of 9 and distribute this undersampling 3 by 3 to the KZ and KY directions. Or we could consider more alternative sampling strategies such as 2D CAIPI or bunch phase encoding. In 2D CAIPI, we stagger this case-based sampling, and this introduces inter-slice shifts in the phase encoding direction, such as this. And this improves the parallel imaging capability because the coil sensitivity information from the collapsing slices are more different now. And in bunch phase encoding, we play an additional GY gradient during the data acquisition. This is a sinusoidal or a zigzag trajectory. And this gives us a voxel spreading effect along the readout direction. And you can see that this spreading depends on the Y position. So in the middle of the field of view, there's less spreading. And as we go further out, this spreading increases. And this is also seen to improve parallel imaging capability. So in Wave-CAIPI, we combine these 2D CAIPI slice shifts with bunch phase encoding in 2 directions. So in addition to this GY gradient, we also have a GZ turned on during ADC. And this spreads aliasing in all 3 dimensions and takes full advantage of 3D coil sensitivity profiles. And this incurs a corkscrew trajectory in K-space. And if you fix a certain Kx, you can see that these circles are also staggered in the 2D CAIPI sampling scheme. So the combination of these GY and GZ gradients with these inter-slice shifts gives us voxel spreading in all 3 dimensions. So the combination of these 3 effects produces this highly spread out Wave-CAIPI image. And in the presence of 3 by 3 undersampling, for instance, this is what we get on the scanner. And starting from this, we try to reconstruct the underlying magnetization. So to try to understand how this bunch phase encoding gradient incurs such spreading, let us for now consider only the GY gradient and ignore GZ and the slice shifts. So we can think of this GY gradient as extra modulation, as dumping some phase to K-space rather than modifying the K-space trajectory. So in image space, what this does is to introduce some point spread function along readout direction, which also depends on the Y position. So in the middle of the field of view, there is almost no spreading. The point spread function is very small. And as we go further out in FOV, we get more and more spreading. And to capture this whole point spread function, we oversample in the readout direction by a factor of 6. And the effect this introduces in image space is to take this image and spread this out in X and Y directions. So to see what happens to a particular voxel, we see that there's a corresponding PSF that convolves it and spreads it out. This can be explained if we start from the signal equation and we get something that looks particularly complicated. Here, wave is our wave image that we acquired. IMG is our underlying magnetization that we would like to recover. And W is our K-space trajectory, which is simply the integration of this sinusoidal trajectory. So if we recognize this inner and outer summations as inverse and forward DFT, we can simplify this a bit more and get this expression. Here, all that we're doing is taking the Fourier transform of the image, multiply it with some phase, and take the inverse Fourier transform. So this is relatively simple, and now we don't have any need for gridding or complicated reconstruction. This is simple Fourier transform and multiplication. And this point spread function is actually what I have shown you before. It depends on the Y and Kx positions and just dumps some phase on the image. So this is what we would do for a fully sampled acquisition. But if you consider accelerated and undersampled acquisitions, For instance, the simplest case would be an in-plane acceleration of 2. Here we would have pairwise aliasing of 2 rows of voxels that are half a field of view apart from each other. We can reconstruct this using a small encoding matrix for each pair and keep doing this until we reconstruct the whole field of view. This is separable and easy to solve, and it provides us with intuition on why these wave improvements, why these wave gradients improve the reconstruction. So if you look at 2 particular voxels that are overlapping in the wave image, we have this voxel spreading effect that spreads this voxel out, and it also helps us with the parallel imaging because now the collapsing voxels are far apart from each other. And again, starting from the previous relation, I simplified this further by calling this PSF at position Y. And what I'm doing is again taking the row of the image at a certain location, multiplied with this PSF, and this gives me my observed wave image. So what happens when we have multiple rows that are collapsing, for instance, looking at positions Y1 and Y2, again, I take these rows, simply convolve them with 2 different point spread functions and add them up to give me my collapsed wave image. On top of this, I also have some coil sensitivity information that I can include. And not only one, but I have multiple coils, for instance, 32 channels. And this small system is my encoding matrix. And by solving this, I can recover the underlying collapse rows using the case space data of the acquired wave image. And I can solve for such each set of collapse rows iteratively using this L-square method. This way, I don't need to form this matrix explicitly, and I can use fast Fourier transforms. So the reconstruction is relatively simple. All we need to do is to solve a linear system, and we get the underlying magnetization. This was only in the presence of GY. What if we turn GZ and the CAIPI 2D shifts? In this case, things remain pretty much the same, except that our point spread function now depends not only on Y, but also on the Z position. And we have shifting the aliasing pattern due to the CAIPI 2D staggering. And these we can account for when we generate our point spread functions. For instance, at 3x3 undersampling, what happens is that the matrix for the encoding corresponds to 9 rows of collapsed image. And the grouping of these rows is also determined by my CAIPI 2D shifts. And the amount of spreading in each row is determined by how much I play these sinusoidal waveforms on the GY and GZ axes. So again, all I need to do is to solve a linear system, which is slightly more complicated. But now I don't need to do any gridding or complicated process. So this was how we reconstruct wave, starting from the undersampled data. And as you recall, we said this point spread function varies as a function of space over the full field of view. But what about looking at a particular voxel? Does it also change within the voxel? So if you look at the top and the bottom of a single voxel, we see that there's also some differential phase modulation. And in image space, we see that there's also a point spread function which has 5 to 10% side lobes relative to the main lobe. And these are in fact out of phase. So if we were to integrate across the whole voxel, we see that these side lobes are very small, 0.5%. So playing these wave gradients does not introduce any blurring or voxel tilting. So now that we know how to do the wave reconstruction, we can look at some in vivo data acquisition, where we compare wave with conventional sense parallel imaging. And to have some ground truth, we acquired fully sampled data, which we then accelerate by a factor of 9. And using this ground truth, we compute root mean square errors, and we also compute 1 over G factor maps. So 1 over G factor is just our retained SNR. So if G factor is equal to 1, it means it's essentially a perfect reconstruction with no noise amplification. We collected data at 3T and 7T with 1 by 1 by 2 resolution, and we covered a whole brain. So at 3 Tesla, at 9-fold acceleration, this corresponds to just 38 seconds of imaging time. And Wave gave us a reasonably clean image, and the root misc error was about 5%. And our Gmax was 1.09. If you recall that perfect reconstruction has a G factor of 1, this means that we essentially have close to perfect SNR retention and no noise amplification. So relative to this, normal sense had quite a bit of structured aliasing in the middle of the FOV, and relative to the fully sampled data, it had about 11% error. You can also see that its maximum G factor is about 2, which means that there is quite a bit of noise amplification, and it only keeps 50% of the SNR. At 70, we have similar results. Wave has about 7% error, and its G factor is again close to perfect. With normal sense, difference to fully sampled data would be about 12%, and again, the Gmax is about 2, meaning it again has poor SNR retention. So it looks like Wave improves quite a bit relative to conventional parallel imaging. So we also compared it to 2D CAIPI and bunch phase. In this case, we acquired actually undersampled data by a factor of 9, and again computed retained SNR. Our data was again coming from 3T and 7T with 1 millimeter isotropic resolution, and this time the acquisition time was about 2.3 minutes for whole brain coverage. So at 3 Tesla, Wave again gave us a clean image with close to perfect SNR retention. 2D CAIPI has a little bit of structured aliasing, and it also does not retain SNR well with a Gmax of 1.8. So bunch encoding seems to be doing okay, but you can still see that it is quite grainy and has some amount of artifacts. Its SNR retention is about 50%. And at 70, all of the methods improve because we basically have 2 times more SNR, as well as a tightly fitting head coil, which improves the parallel imaging. And in this case, Wave is again close to perfect SNR retention, while 2D CAIPI and bunch encoding has close to 2-fold more G factor. So now I want to switch to a totally different topic. It is about susceptibility of tissue. And at the end of the talk, I'll try to tie these two topics together. So this susceptibility I denote with chi, and this is the amount of magnetization a material feels when it is immersed in an external magnetic field. So suppose I have a B0 facing up. Materials whose magnetic moment aligns anti-parallel to this field are called diamagnetic, and their susceptibility is negative. And materials that align parallel to the external field are called paramagnetic, and their susceptibility is positive. So water, for instance, is diamagnetic with susceptibility of about -9 ppm, whereas iron is strongly paramagnetic, and in fact it is called ferromagnetic. So susceptibility of brain tissue is about also -9 ppm because in structure it is similar to water. And tissues with increased iron deposition are relatively paramagnetic, and their susceptibility is going to be more positive. And this we can use to investigate excessive iron concentration in a variety of neurodegenerative diseases such as Alzheimer's, MS, and Parkinson's. So susceptibility can serve as a biomarker for such diseases. Unfortunately, we cannot measure the susceptibility on the scanner directly, but what we can see is magnetic field perturbation due to variations in tissue susceptibility. And this field perturbation causes a change in the observed MR signal phase. So what we can measure, oops. Let's see. Okay, what we can measure on the scanner is the phase, and from this we try to compute the underlying susceptibility. Yes. So the method in which we estimate the tissue susceptibility is called a quantitative susceptibility mapping, or QSM. And it has several important applications, such as enhancing tissue contrast, estimating blood oxygenation level, and quantifying tissue iron concentration. And estimating the susceptibility from the observed phase involves solution of a linear system. So here F is our discrete Fourier transform, D is a susceptibility kernel, and delta is simply our phase normalized by the echo time and the external field strength. So again, we measure the phase, and from this we would like to estimate the susceptibility by solving such a linear system. But this inversion is a bit difficult because of the zeros in the susceptibility kernel. So in K-space, this is what it looks like, and you can see it has zeros on this conical surface. And this effectively undersamples the Fourier representation of the susceptibility. But this undersampling is due to physics, and it is not something in our control. So what we can do is try to naively invert this kernel. But even if we look at the log space, you can see that it diverges along this magic angle. So we cannot really do this inversion directly by using the inverse. And what we would like to do instead is to pose this as an inverse problem and apply regularization. Before we can do that, however, there are several processing steps. It starts from the MR signal phase and yields the tissue phase. So first we want to mask out the skull, and we can use FSL bed for this. Then we would like to unwrap the phase using FSL prelude, for instance. And finally, we would like to remove the background phase. So there is phase accrual due to air tissue and air bone interfaces. And this background component is about 10 times larger than the tissue phase we're interested in. So starting from this total phase, we can try to estimate this background contribution and subtract it off from the total phase. And this gives us the observed total tissue phase. And you can see from the scale that it is about 10 times smaller than the background component. So it is this tissue phase that we were interested in, and we will use this to try to solve for the underlying susceptibility distribution. Again, we would like to find the susceptibility that matches our phase. And we can use some prior information while doing this. And it is that the susceptibility is tied to the underlying tissue's magnetic properties. So it should vary smoothly across space. We can employ regularization that encourages such smoothness within the tissue boundaries, but avoids smoothing across boundaries. And this we can do by using such a convex program. So the first term is my data consistency. I would like my susceptibility to match the phase. And my second term reflects my prior belief, and it is the regularizer. So here G is a spatial gradient operator in 3 dimensions. M is a binary mask we derive from the magnitude image, and it prevents smoothing across edges. And lambda is some regularization parameter that determines the amount of smoothness that we would like to dial in. So this we can solve by simply taking its derivative and setting it to 0. And this entails solution of this linear system. But this is a large problem, so we would like to solve iteratively using a method such as a conjugate gradient. And without magnitude weighting, setting M to identity, we came up with a way to do this inversion by using 2 FFTs. So it's very fast, and for the whole 3D volume, it takes a couple of seconds. So using this inverse as preconditioner for this conjugate gradient, we also propose a fast solution to the original problem with the magnitude weight. And we saw this improved computation speed quite a bit relative to existing solvers. So now we have a fast solver for susceptibility, and we have a fast data acquisition technique. So we combined the two and used Wave-CAIPI for QSM acquisition. In this case, we compared the phase and susceptibility maps we compute from Wave-CAIPI, 2D CAIPI, and bunch phase encoding. And the data that I use is the same, gradient echo at 3D and 7T with 9-fold acceleration and 1 millimeter resolution. And for phase processing, we use a fast unwrapping algorithm and a fast background removal method called SHARP. And the combination of these is about 14 seconds of computation. And for susceptibility inversion, the fast L2 regularized reconstruction takes about half a minute. So for the whole 3D volume, phase processing and susceptibility inversion takes less than a minute together. So using these at 3T, a 2D CAIPI gave us this tissue phase and susceptibility reconstruction. And you can see that in the middle of the brain, especially quite a bit of structured aliasing artifacts. And also it is looking a bit grainy due to poor SNR retention. So with bunch encoding, you can also see some ringing artifacts, and the SNR is not quite nice. And with Wave-CAIPI, we get a clean-looking image with high SNR. So if I toggle between the two, you can appreciate the difference. And finally, at 7T, we repeated the same experiment. And this is the tissue phase and susceptibility we get from 2D CAIPI. You can already see it has improved quite a bit over 3T. But there are still some artifacts in the phase that also reflect the susceptibility map. And with bunch phase, it looks almost free of any artifacts, except for some subtle ringing and far from perfect SNR. And with Wave-CAIPI, we get very good-looking phase and susceptibility reconstructions, free of artifacts. So if I toggle again, you can hopefully appreciate the difference. So to sum up, we proposed Wave-CAIPI acquisition and reconstruction technique that allows a highly accelerated 3D imaging. This offers twofold improvement in G factor and image artifact penalties when compared to 2D CAIPI and bunch phase encoding methods. And we deployed this in 3D GRE imaging, and it allowed a 9-fold acceleration with close to perfect SNR retention, both at 3T and 7T. And when we combined this with fast phase and susceptibility methods, it enabled QSM at 1 millimeter resolution in just 2 minutes. And with this, I'd like to finish, and thank you for your attention.